Okay, hi, welcome everyone to this week's Lattice Colloquium. And just a reminder again that since we have fairly large audiences, you're muted by default during the talk, but please don't let that stop you from asking questions. You can post questions to the chat or use the raise hand feature under the reactions button, and our moderator, Dan Hackett, will monitor and interrupt for questions at appropriate times. And then after the talk and after the questions, we'll have a Zoom social half hour in small groups. So please stay if you'd like. And of course, the slides and the recordings of this talk and of all the past talks are available on the series website. So today we're delighted to have Raghav Govindjat from the Perimeter Institute in Canada to speak about probing holographic dualities with lattice supersymmetric Yang-Mills theories. Before beginning his postdoc at Perimeter in September 2019, Raghav completed his PhD at Syracuse University, and as well as the work we'll talk about today, Raghav's interested in tensor network descriptions of gauge theories and the thermal phase structure of supersymmetric theories. So thank you very much. Looking forward to your talk.
Okay, thank you so much, Fiala, for the invitation to give this talk. And I'm really happy to be talking at this MIT Lattice Colloquium. So today I'll talk about uh, how we can probe holographic dualities using supersymmetric Yang-Mills theory on the lattice. This is work done in collaboration with Simon Cattrall, Joel Geet, David Shake, Anos Joseph, and Toby Weissman. So let me just briefly mention what this talk could also have been. Since I was invited to give this talk, I have two broad research interests. One is what you will hear me talking about in this talk. Another is related to the tensor network approach to spin models and lattice gauge theory. So recently in the past couple of years, and as part of my position at Perimeter, I have also been working on tensor renormalization group. And this is just a new decade-old approach in which uh, an efficient way of dealing with spin models with discrete or continuous symmetries, and also some lattice gauge theories like two-dimensional and three-dimensional U1 gauge theories, or say two-dimensional SU2 gauge theory with Wilson action and fundamental matter. The I eventually got interested in this approach because this has the potential to substitute the conventional Monte Carlo approach, which we use for gauge theories and other systems. Since this has no sign problem in the sense that this is completely a deterministic approach, there's no stochastics or sampling involved. However, this is not free from all the troubles. For example, uh, uh, studying higher dimensional field theories using this method has been very difficult. So for example, people have studied 2D U1 gauge theory with theta term, and people are also looking into two-dimensional and three-dimensional O2 gauge theory spin models at finite chemical potential, which is not possible using conventional Monte Carlo method. Some of the work which I've done is these papers, and some are upcoming. So I'll not talk about this, but I'll talk about lattice supersymmetry gauge theories, and I'll give an introduction into how we can discretize and study certain supersymmetry gauge theories on the lattice. And I'll discuss what opportunities open up for the lattice studies at strong couplings and large N. Basically, what I'll talk about is known as the 't Hooft limit. So what happens to these lattice supersymmetry gauge theories in the 't Hooft limit in various dimensions? Actually, my talk will cover 0 plus 1, 1 plus 1, 2 plus 1 dimensional supersymmetric gauge theories. And I'll mention how it can refine or sharpen our understanding of holography and string theory. I'll also mention some future prospects which I hope we can achieve in the coming years or so, so that we can get much more interesting results than what we have right now. Okay, so let me just give a brief outline of my talk. First, I'll describe what do we mean by general holographic principle, and then I'll talk about holography for 0 plus 1 dimensional matrix model, just quantum mechanics. And then moving on from there, I'll talk about the higher dimensional super Yang-Mills theory in all dimensions, including 4. I'll say the least about 4-dimensional super Yang-Mills theory, but I'll mostly concern with the lower dimensional, but the construction which I'll mention is for the general n equal to 4 super Yang-Mills theory on the lattice. Related to that, I'll mention the phase structure of a supersymmetric matrix model, and that will be at finite couplings and large n. and at finite temperatures. Then moving on, so this is a 0+1 dimensional supersymmetric matrix model. Then I'll move to 2-dimensional and 3-dimensional super Yang-Mills theory on the lattice and describe the thermodynamics of the dual black branes in that in the low energy super string theory. So what I mean by basically dual black branes are, so in string theory we have black holes, they are higher dimensional black holes, and they are represented by, they are talked about in the sense that they're called as black branes. So I'll describe how we can interpret black branes uh, uh, in the sense which we are familiar with, for example, the 4-dimensional Schwarzschild black hole and so on. And I'll mention some future directions. So what is the basic idea of holography? So the basic idea of holography goes back to, I think, the work from the 70s because of Stephen Hawking and Jacob Bekenstein. What this idea basically tells us that is that the quantum gravitational theory in higher dimension, say d+1 dimensions, is related to some quantum field theory, and that quantum field theory is without gravity in one lower dimension on its boundary. So this is a correspondence or a dual relation between a d+1 dimensional theory with in full glory, that is quantum gravitational theory, and a theory without gravity in a lower dimension. Now, why is this important? It is important because there are various approaches to quantum gravity, and one thing most of those approaches agrees with, or they believe widely, is that any consistent theory of quantum gravity should admit a holographic description. So understanding holography has been a very important problem in physics for the past 25, 30 years. So we start with this famous formula of black hole entropy. And I think this is one of the most famous formulas in physics because you can see that there's Boltzmann constant. So for example, I draw 4 circles and the black hole entropy sits at the intersection of those 4 circles. So by 4 circles, I'm denoting the statistical mechanics given in terms of Boltzmann constant, the relativities in terms of speed of light, and then gravitational theory in terms of g, and quantum mechanics in terms of h bar. So this is a formula which connects all those, and the black hole entropy is sitting right at the center. And it makes more sense because the first hint of holography was also from black hole. So black hole is an important object in any theory of quantum gravity because we have to understand them carefully. Now, holography, when it was introduced in the 70s, had nothing to do with supersymmetry. Supersymmetry was developed separately later on in the 70s as a different framework of extending our standard model of particles. So what I like to say about supersymmetry is it's elegant, beautiful theory because you can perform exact computations in that, but it is certainly broken and has not been experimentally observed. So we know this standard model particles, quark, leptons, force carriers, and there's supersymmetry extends those standard model particles by introducing other particles, none of which we have seen till now. But as I will mention in the next slide, supersymmetry has not, even though it has not been experimentally observed, it has played a very important role in the development of something called ADS-CFT. So what is ADS-CFT correspondence? ADS-CFT correspondence was introduced by Maldacena in 1997. Now, there was always this idea that there's holographic principle at play, but ADS-CFT is the first concrete example. When I talk about holography, you have to specify 2 things. What is the theory in the bulk and what is the theory at the boundary? ADS-CFT did that for the first time. It said that the theory in the bulk is for example, you can think of it as a quantum gravitational theory in an ADS space-time. And then the 4-dimensional theory on the boundary, which is denoted by this boundary here, which is the boundary of ADS5, is some special conformal field theory. It's not just any simple QFT. It's a very special conformal field theory with some amount of supersymmetry. And this theory on the boundary is what we call n equal to 4 super Yang-Mills. So this ADS-CFT correspondence is a correspondence between some 5-dimensional quantum gravitational theory, and some four-dimensional field theory, which is sitting at the boundary. In the limit of large number of colors, so for example, if I take we usually associate that gauge, if some gauge theory, for example, like QCD has SU3 symmetry group. Now we can, using the Thup's idea of large n limit, we can take the large n limit and then take the lambda, which is the Thup coupling, to be very large. So in that case, the quantum gravity theory in the bulk reduces to Einstein-like gravity, which is just a low energy approximation. So for example, this duality says that there's certain relation, but it is best understood right now in the limit where the bulk theory is like Einstein gravity. Because if the bulk theory is not like Einstein gravity, then it is difficult to do calculations. So the best proofs or the uh, work has been done in this limit, which is the large and strong coupling limit. But this is not just ADS5 or CFT4, which I'm talking about. There's nothing special about, say, the pair of 4 and 5 dimensions. In fact, just within a year of the original paper, Maldacen extended this idea, Maldacen and co-authors extended this idea to supersymmetric gauge theory, maximal supersymmetric gauge theories in less than 4 dimensions, even though they are not conformal. So they are not conformal in the sense that n equal to 4 super Yang mills is a conformal field theory. There are no scales. The beta function vanishes at all loops and other nice properties. But when you go to the supersymmetric gauge theory in D less than 4, it is no longer conformal. And one of the most studied pairs, in fact, apart from ADS5 and CFT4, is ADS3 CFT2. So there have been many exact calculations in, for example, related to entanglement, entropy, and other quantities in, say, for example, CFT2, which matches exactly with ADS3. So there is also this ADS3 and CFT2. So there's nothing special about 4 and 5 dimension. It's probably the mostly referred in the literature, but it extends to all dimension. That is the important point. So what is the exact conjecture in or in a general dimension? So the exact conjecture in the general dimension goes something like this. It says that the maximally supersymmetric Yang mills. By maximally supersymmetric, I just mean that it has the maximal possible number of supercharges. So if I go to any number of dimension, there's some number of supercharges which you can have with helicity, maximum helicity equal to 1, because you want a theory, supersymmetric gauge theory, without gravity. So you don't want to include any gravity or other things. So with maximum helicity 1, you can at most maximally supersymmetric Yang mills will have 16 supercharges. So that is what I mean by maximally supersymmetric Yang mills theory in P plus 1 dimension is dual to dp branes in supergravity in some special limit, which is exactly the limit I discussed before, large n and strong coupling. Strong coupling, I just mean lambda is much greater than 1. And they are dual because the supergravity solutions are just like black in P, corresponding to this P plus 1 super Yang mills theory, are known as black P brane. It's just a string theory terminology, which we don't want to need to go into. We can just think of it as some higher dimensional black hole version in string theory. So when I say, for example, black 3 branes, what I mean is a black hole which has world volume equal to 4-dimensional, right? Because P is just the number of spatial dimension. So when I say black 3 brane, I mean a black hole which lives in a 4-dimensional world. So that is a black 3 brane. If it is a black 7 brane, it is in an 8-dimensional geometry. So that is just like what I mean by black P brane. These are just higher dimensional string theory terminologies for the usual black holes, which we are familiar with in 4 space-time dimensions. Now, when I mentioned this, that the duality is in P plus 1 dimension, there are a zoo of super Yang mills theory. In fact, what happens is when we talk about low energy string theory or say supersymmetry, you can have supersymmetric gauge theory in any dimension from d equal to 1 through d equal to 10. So there are a lot of supersymmetric theories. So which one are important for us in context of holography, and that is where we want to go. And the starting point for such a case of what theories are important for holography starts from the action of 10-dimensional n equal to 1 super Yang-Mills theory. So this is the action of the 10-dimensional n equal to 1 super Yang-Mills theory. Note that the 10-dimensional n equal to 1 super Yang-Mills also has 16 supercharges. So it's also a maximally supersymmetric Yang-Mills theory in that dimension, n equal to 1. And the action is just given by this term. It's just a 10-dimensional. So you have this volume element here. And there's just two pieces. There's this gauge part, and then there's a fermionic part. So for example, this is S boson or something, and this is S fermion, and they are related by symmetries. So this is one of the simplest action which we can write down in 10 dimension, and it appears that this action is supersymmetric, which we can show, and it is based on different properties of spinor and how they act in any dimensions. So psi is just a spinor with 16 real components, which I write here, and D is the usual covariant derivatives. Now, I mentioned that 16 supercharges is in D equal to 10 is this n equal to 1. So what happens when I dimensionally reduce? When I dimensionally reduce, for example, D equal to 6, it is known as n equal to 2 super Yang-Mills. That is also maximal in this dimension. This dimension. So all these theories are maximal because they have 16 supercharges. So as you can see, in D equal to 4, n equal to 4, this is the usual n equal to 4 super Yang-Mills theory, which we call. So all these theories on this line are basically admit some holographic description because they are all maximal. There are also minimal supersymmetric gauge theories. So minimal is when we just have 4 supercharges and they are D equal to 4, n equal to, in 4 dimension, it's n equal to 1 super Yang-Mills theory. And for example, in n equal to 2, it's in D equal to 3, it's n equal to 2. So for this talk, I'll only consider these theories, and especially these three, in D equal to 2, D equal to 3, and D equal to 4, maximal supersymmetric gauge theories. Okay, so what exactly is n equal to 4 super Yang-Mills theory? So I just give a one slide introduction to this model because it is one of the cornerstone of holographic conjecture, and it's a very interesting theory which we use all the time to understand about black holes in string theory and so on. So this theory, as I mentioned, can be obtained by dimensionally reducing the 10-dimensional super Yang-Mills theory. So you start off with n equal to 1 in 10 dimension, and then basically reduce to 4 dimension by setting the derivatives along the 6 spatial directions equal to 0, and you get this 4-dimensional theory. This theory is a conformal field theory. The beta function vanishes to all loops, and this consists of 6 scalars. Now, these 6 scalars are just coming because I'm dimensionally reducing from 10 dimension to 4 dimension. If I dimensionally reduce from 10 dimensions to 2 dimensions, I get 8 scalars. So the number of scalars tells you what parent theory you're reducing from, basically. It has 6 scalars, 16 real fermions, and they're all massless and in the adjoint representation of the gauge, SUN gauge group. This is arguably the simplest interacting QFT without gravity in 4 dimensions. The action has kinetic term, Yukawa term, there's a quartic scalar commutator terms. We don't want, there's no point going into the details of the action, but these are the terms in the action. And then they're all related by supersymmetry. The important thing is that the super conformal algebra includes what we call SU4 or spin 6, and that is the R symmetry group. So for example, this is the R symmetry group. So R symmetry is like a symmetry in supersymmetric gauge theories where the supercharges can be, so if you act, they transfer one supercharge to another supercharge because there are multiple copies of those supercharges. So these R symmetry transform one supercharges to another supercharges. And apart from that, since this is a SU4, this is a 4-dimensional field theory, this has the usual SO4 Euclidean group. The interesting thing about n equal to 4 is that if I put this theory at finite temperatures, the supersymmetry is explicitly broken by thermal effects. And in that limit, it is sometimes also dubbed as close cousin of QCD. Now we can argue that n equal to 4 is not physical, there are scalars and other things, But the basic idea is that the gauge fields are sit in the adjoint representation, and at finite temperature, SUSY is broken. So there is definitely some window in which it is very similar to QCD, but obviously it's not QCD. But at finite temperature, it's very similar in the sense that, for example, if I look at the free energy of QCD at high temperatures and the scaling with temperature and so on, it's the same in n equal to 4 also. It goes like T4 and so on. So we want to study this supersymmetric gauge theory on the lattice. Now, studying supersymmetric gauge theory on the lattice is even before starting, it's already like has a lot of difficulties, because if we just look at this basic SUSY algebra. So SUSY algebra is the extension of the Poincare algebra, which we are familiar with in four-dimensional field theory. Supersymmetric algebra has something like the anti-commutator of Q and Q bar, which is given in terms of p mu, where p mu is like the momentum. But we see that this is already broken on the lattice, because p mu generates infinitesimal translations, and on the lattice we only had finite translations. So this is already broken at the classical level on the lattice. So it seems completely hopeless to study supersymmetry on the lattice. So there is one alternative, which is due to authors mentioned here: Cohen, Kaplan, Katz, Unsal, Cattrall, and Sugino. So they came up with different approaches during 2000 and 2008. But all these different approaches are in some sense equivalent, in the sense that they all give you some supersymmetric gauge theories, which you can study on the lattice. So what is the basic idea? The basic idea is that you don't worry about keeping all the supersymmetries of the continuum theory on the lattice. You only preserve a subset of this algebra. You only preserve a subset of this algebra on the lattice, and then check or try to reduce the number of counter terms, and try to reduce the fine tuning to such an extent that as you take the continuum limit, the other supersymmetries are restored. So in this sense, this is one of the possible ways in which uh, 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 there has been a lot of success in studying supersymmetric gauge theories. So this is a nice review in which all these methods are mentioned. And I'll briefly discuss what is the basic idea. But this is what we are going to, the results which I show you in this talk are based on this idea, that we preserve a small subset of the entire symmetries of the continuum gauge theory, supersymmetric gauge theory on the lattice exactly, and then hope that as we take the continuum limit in some proper manner on some special, in some special on lattices, reducing the number of counter terms, so that the fine tuning is minimum and we get to the correct continuum theory. But still, with this method, we cannot study all the supersymmetric gauge theories. Now, the problem that is related to is because when I want to preserve some subset of the supersymmetry, the one thing I need to be completely sure of is the continuum theory should have sufficient number of supercharges, in the sense that if the continuum theory is itself very minimal, then studying it on lattice is impossible, because if you have, say, only 2 supercharges or 4 supercharges in the continuum in some dimension, then keeping a fraction of it is almost impossible. So you want to have as much supersymmetry in the continuum field theory as you can have, and then try to keep some subset of that. So that leads us to the situation that we should definitely have at least 2 to the power d number of supercharges in the continuum. So anything which has less than this in the continuum, we cannot study. For example, if I go to, for example, say the d equal to 4 n equal to 1 supersymmetry, which has 4 supersymmetries in d equal to 4, we cannot study that on the lattice. So this is a no. In this sense, this is also not possible to study on the lattice. Obviously, in d equal to 2, it's all possible, because d equal to 2, anything with 4 or more works. So you can have 4 supercharges. Here you can have 8, you can have 16, and all 3 are possible to study on the lattice. So these are just the different approaches. So one is known as orbifolding and one is known as maximal twist. What we are going to use in this talk is the maximal twist approach. But you can see that since all these methods are equivalent, what works for one of them works for the another as well. So for example, n equal to 1 in d equal to 3 is impossible to study on the lattice. And similarly, the only thing we can study in 4 dimension is the maximal supersymmetric angles. We cannot study these two. But there has been some progress of studying n equal to 4 superangles theory in 4 dimension. So with our approach, it's not possible, but some work by German group, which is mentioned here, have tried to study this theory, and they have to deal with fine tuning head on, in the sense that the subset which we keep, which reduces the effort to take the continuum limit and reduce fine tuning, is completely absent for them, and they have to do all the fine tuning and other things in their computations. So it's harder, but probably in n equal to 1 superangles case, it's simpler because the R symmetry group is not very complicated. So there was, in fact, I just want to mention that there was an earlier talk in this colloquium a couple of months ago, which discussed especially this part, n equal to 1 in 4 dimensions. So you can refer to that if you're interested. So what I'll talk about is lattice n equal to 4 superangles theory. And this is based on the idea that we are going to do a maximal twist, which is topological twisting of a supersymmetric gauge theory. And what this does is, this gives us a zero form supercharge. So for example, as I mentioned, there are 16 supercharges in the continuum in 4 dimension. Now, what we want to do is we want to break that into P forms, in the sense that we want to break that into 0 form, 1 form, and 2 forms. So if we do that, then we can put the 0 forms on the lattice sites, we can put the 1 form on links, and we can put the 2 form on the plaquettes. So this twisting procedure, or the maximal twist procedure, gives us this P forms, which can then be discretized and studied. The basic idea is straightforward. The basic idea is that you start with the S symmetry, R symmetry group of n equal to 4 superangles, which is SO6, and then you take a subgroup of that SO6, which is SO4, and then you already have a SO4 Euclidean because you're in 4 dimension. So you do a cross of SO4 Euclidean and SO4 R symmetry group, and then take a diagonal of that, and that gives you something which we call twist. So twisting is a procedure which works very well in flat spacetime. On curved spacetime, it's more tricky, but the basic idea is that you change the spinner, which are so you change the spinners, which spin half objects, supercharges, into spin zero objects, integer spin objects, and put them in P forms. And that is what this process of topological twisting is. And this goes back to Witten and other authors in the 80s. So even after we are starting with a continuum theory and doing a topological twist of that theory to get some nilpotent supercharges, that is zero form supercharges with squares to 0, that is q squared gives 0. Even that is not sufficient to reduce the fine tuning which we need to do in order to retrieve the continuum theory. Another ingredient of this construction is that what we have to use is something called A4 star lattice. So hypercubic lattices are very familiar in QCD and other study of gauge theories. But this A4 star lattice is slightly different, in the sense that, for example, I can just show you here a smaller 2-dimensional version of this A4 star lattice, which is just a triangular lattice in 2 dimensions. So the basis vectors are not orthogonal to each other. The reason why we work with this A4 star lattice is, this A4 star lattices map very naturally to the twisted formulation of supersymmetric gauge theory. So when we twist the supersymmetric gauge theory, this A4 star lattice has 5 basis vectors. So this has 5 links, basically, A4 star lattice, and it is very natural to lay down the fields on the lattice if we use this lattice. So for example, the simplest way to understand this is, I mentioned that n equal to 4 super Yang-Mills has 6 scalars, right? So if n equal to 4 Yang-Mills has 6 scalars and there are 4 components of the gauge field, so you have a total of 10 field components. So if I work on A4 star lattice, which is 5 links, it's very natural in the sense that each link can be associated to a pair of a component of the gauge field and scalars. So for example, that I cannot do on a hypercubic lattice, for instance. So that is why, and for various other reasons, this lattice is special, and that is what we have in the construction of n equal to 4 superangles. But the important thing is that the basis vectors are not orthogonal. So we have a public code for this n equal to 4 superangles theory. So this is a very small community, and large scale lattice calculations are still in early days. But we have a parallel 4-dimensional arbitrary n code, which is available on GitHub. There's a version, updated version, we should follow on CPC, computer physics communications soon. But the basic idea is that the action is pretty complicated because I have skipped over several things which add to the complexity of the problem, in the sense that we have flat directions in the supersymmetric gauge theory. So we have to add some terms to stabilize the numerical calculation and then take the zero limit of those terms. So some symmetry breaking terms, which we have to tune to zero carefully. But the basic idea is this code evolved from the Milk lattice QCD code and was presented in this. So this is what we usually use when we study holographic conjectures on the lattice in various dimensions. So as nice as it sounds, the lattice n equal to 4 is extremely hard. And it seems that it is almost certainly the case that it is not possible to study at large n and lambda in practice using classical computers. There are various reasons for that. One of the prime reasons is that as we go to strong coupling, we see that there's a sign problem. And that sign problem is pronounced even, forgetting about taking the large n limit, even if you work at n equal to 2, 3, and 4, and things like that, even for lambda greater than 5, we have a sign problem. And there are additional complications because of this being a super conformal field theory with no scales. So no scales is bad in the sense that whatever lambda you put, that is the lambda you get. You don't have any flow. You don't have the coupling flowing with the scales. So it's hard in that sense. And also because this theory has moduli, so you have to be completely sure about what is the point in the moduli space around which you're expanding around, and whether you're getting the right super conformal fixed point and so on. But since it is hard in 4 dimensions, the natural thing to do is go to lower dimension and see if it is any easier in those cases. So that is what my research has focused over the years. I have focused on lower dimensional version of this theory, n equal to 4, with maximal supersymmetry, because I already mentioned that maximal supersymmetry can be in any dimension from d equal to 1 through d equal to 10. So just go to d equal to 1, 2, and 3 maximal supersymmetric gauge theories and study them. And they are non-conformal, as I already mentioned, and the computational costs are under control. And sign problem does not seem to play such a big role in those lower dimensional theories. And those theories are also interesting for black hole physics. So I'll present some results related to 0 plus 1 dimensional matrix model quantum mechanics, which is known as BFSS and BMN models. And then I'll present some results from 1 plus 1 and 2 plus 1 dimensions. Okay, so the matrix model, which we have in 0 plus 1 dimensions, is obtained from the dimensional reduction of n equal to 1 superangle theory down to just the time direction. So we have 9 scalars in this case because we are reducing 9 directions. So we get 9 scalars. This has SYM gauge symmetry, and there's a SO9 internal symmetry group, just because you can rotate all those scalars to one another. So there are 9 scalars. So they come with a SO9 R symmetry group, or SO9 symmetry group in this case. This is the simplest holographic gauge theory because this is just in time direction. There's just one dimension. And this has a well-defined gravitational dual, which was most famously conjectured in this work by Banks, Fischler, Schenker, and Susskind in 1996. And this is known as BFSS. So this is the action for the BFSS model. We have the kinetic term for the scalars, and then we have a commutator term, which is this. And then we have 2 fermionic terms, which is kinetic fermionic term, and the another is Yukawa. And these indices I and j are running from 1 to 9 because there are 9 scalars. scalars are represented by X in this action. So this is the action for BFSS model. There's another supersymmetric the model which people have studied, which has a well-defined holographic dual, and that is known as BMN model, after the authors Bernstein, Malus, and Anastase. And that is starting with this BFSS action, you add some more terms, uh, and that term just breaks the SO9 symmetry down to SO6 cross SO3. So what you have is, in the original theory, you have 9 scalars, but in the BMN model, you take those 9 scalars and make 2 groups. You split them into 6 scalars and 3 scalars and give them different masses. So what happens is, when you give them different masses, the gravity dual changes. And then you end up with something called a BMN model. The BFSS model has a single phase, in the sense that if you go to any value of coupling, you will always be in the deconfined phase. I'll mention later on what I mean by deconfined phase. But BFSS has a single deconfined phase. But BMN model admits a deconfinement phase transition, in the sense that we see that it goes from a phase where the center symmetry is broken to a phase where center symmetry is restored. So BMN is more interesting in that sense because it has a rich phase structure. I just want to mention some state-of-the-art lattice results for BFSS, which is obtained by a Japanese group. And this is the reference. What they have done is they have compared to some energy density in the super Yang-Mills theory against temperature, and they see a perfect agreement with a black hole in string theory. So for example, when you plot this against temperature, you see that all the points are the results from lattice simulation, and this solid curve is the supergravity, which is just mentioned as Sugra here. So this is the leading order supergravity, this is the corrected one. So when you are at finite temperatures, this corrected curve. When you go at 0 temperature, this they all become the same up here. So this agreement is striking, in the sense that this is a direct proof that holography in this system, in the 0 plus 1 dimensional system, is actually true, in the sense that the holographic principle has been tested using non-perturbative case theory computations, which is highly non-trivial. And all these computations are at a very large value of n. So I should mention here, how do they get such nice results? The nice results they get is because they explode till n equal to 32. So this is SU32 gauge group, which they are working with, and they took the continuum limit. Taking continuum limit in this case is trivial because it's one dimension, but the nice results are because they have n equal to 32, and that is obtained because their code has parallelizes over the matrix degrees of freedom. So for example, parallelization over n is very essential to accurately reproduce the holographic behavior in this model. As I mentioned, we use the Milk lattice QCD based code to do our supersymmetry gauge series, and we have not yet explored this parallelization over matrix degrees of freedom or the rank of the gauge group. What we have is just the usual parallelization over lattice volume, and that is not very useful in 1D. So that is one of the things which we want to study in the future. Try to make the parallelization over the matrix degrees of freedom. So I'll show you. I'll show some results related to BMN matrix model, and BMN matrix model now is just given by this action, which is the BFSS action, and then we have mm, the mu terms which break the SO9 symmetry, and there's this cubic term in X scalars, which is known as the Myers term, and this is related to the fuzzy sphere structure of the vacuum in this model. And there's another term, mu dependent fermionic term in there. The basic idea is that when I take this G to be large, it admits some holographic description. So G has to be large in the sense that lambda over mu cube. This is a dimensionless factor. So G is dimensionless. And if G is much greater than 1, we have a holographic description. So there is results which are available at G equal to 0, because at G equal to 0, you can do expansion in large, you can use large mu limit expansion. And then this is the critical temperature which you have. So for example, when lambda equal to 0, you have a critical temperature of the deconfinement transition equal to this value, 0.076. So I mentioned that the BMN model has this interesting phase structure. So what does the phase structure look like? The phase structure is something like this: deconfined phase, confined phase. At strong values of G, this is the gravity limit. This is the weak perturbation theory limit, G equal to 0. So it's 0, the T by mu critical temperature in terms at G equal to 0 is 0.076. And at very strong values of G, which is a holographic regime, it goes to some value. But all these dashed lines are unknown. We don't know what exactly happens in the dashed line. So that is a perfect avenue for any lattice computation. So we eventually wanted to do a lattice computation which starts with here and eventually goes as far as we can, eventually agreeing to this supergravity limit. So if we can do something like that, it will be a test of holography so that we can reproduce this from first principle lattice computations. So the basic idea is that the everything around intermediate regions about the thermodynamics, about the critical coupling is basically unknown. So our lattice computations want to reproduce, get to those results. So this is just a brief summary of what we want to do. We want to understand the critical temperature and we want to reproduce the thermodynamics. So let me just show here some preliminary plots which we have. As I mentioned, we go to G equal to 0. So we go to very small values of G and we see that this agrees with the perturbative predictions. And as we increase the value of G, it goes to gravity prediction. This is a preliminary plot. And this is just with n equal to 8. So we have been able to do much higher n than this. We have been able to go to n equal to 16. So this is the basic idea. It starts from this and then tends to this. So this is what we want to study in more detail. And this is an upcoming work. So how do we see this phase transition? We see this phase transition in the Polyakov loop. So you have anti-periodic boundary condition for the fermions and you measure the Polyakov loop. So if we go to very large values of T by mu, the Polyakov loop is almost very large in the sense that it's close to 1. And then as you go to small values of T by mu, it goes through a phase transition. So for example, as I increase the coupling, we can see that the phase transition for this case is somewhere here, somewhere here, somewhere here, and so on. So it goes to higher values as expected with increasing coupling. So this is a positive result we see directly from the lattice. Now this was 0 plus 1 dimension, which was some preliminary work. But now I want to mention the works which we have finished related to 1 plus 1 dimensional super Yang-Mills theory and 2 plus 1. So the basic idea is the same. You go to 1 plus 1 dimensions now. And now what we have is we have anti-periodic boundary conditions. So fermions have SUSY breaking boundary condition. SUSY breaking boundary condition is just the anti-periodic boundary condition. And then we start from the 4-dimensional theory, which is discretized on a A4 star lattice down to 2 dimensions. So we basically now have a triangular lattice in some sense, which is A2 star. And then this theory also has a deconfinement phase transition. So what is deconfinement phase transition on the gravity side? So if there is a deconfinement transition on the gauge theory side, the dual on the gravity side is a transition between a localized black hole and a black string. So you can think of localized black hole as something like, if I have something like this, a localized black hole is something which is localized to a very narrow region. And a uniform black string is something which is extended over a long, has a cylindrical topology. So what happens is the center symmetric phase is like a uniform phase, and a center symmetry broken phase is like a localized phase. So center symmetry broken and the Polyakov loop value determines what kind of transition which we are seeing. And these transitions are also seen in, say, for example, one placket 2D pure lattice gauge theory, which goes by the name of Grosspitt and Warrior transition. So this is the transition which we want to study. Now, we can only study this transition when we satisfy certain limits, and that means that we should have the coupling which should be much greater than 1. So for example, this coupling was defined here. So lambda is dimensionful in 2 dimensions. So we construct a dimensionless quantity, which is Rx and R beta. And then alpha is just L over beta. This is the aspect ratio of the lattice. So you want to change the aspect ratio of the lattice and see the center symmetry broken and the center symmetry intact phases. And the gravity prediction says that it should happen at this, on this curve. So that is a result we want to reproduce using lattice computation. So in 2 dimensions, which we studied, we could do a lattice of 250 sites with SU16 for different aspect ratios of the lattice. And what do we see? We expect something like this. This is the cartoon which we expect, in the sense that when this is very small, this is like a deconfinement transition. When we go to gravity phase, which is the 2 different gravity phases here, and this is the deconfinement. And as I mentioned, this is the prediction which we have from the uh, supergravity results. And now we mentioned the lattice results on the right side. So as we see, there are huge errors on as we go to strong values of RL, but the basic idea is it agrees with the deconfinement transition for small RL. And as we go to large RL, we see some deviation from the red curve, but that is just because we have huge errors, and also because we are not strictly in the large n limit. And these critical couplings show up like this in the Polyakov loop. So here it is n independent, n independent, n independent. And as soon as you increase n from 6 to 9 to 12, you see that there's a transition which starts to happen here. So this is 0.22 where the transition happens. And this is for alpha equal to 4. So alpha equal to 4 is just this. This is alpha equal to 2, and this is alpha equal to 1. So these are slices of aspect ratios in R beta and RL plane. So we kind of see the gravity results here, and we also see the gravity results for the for the thermodynamics phase, in the sense that this is the prediction from the supergravity results, the dashed curve, and these are our lattice results for SU12, SU16, and again SU12 on a bigger lattice, keeping the aspect ratio fixed at alpha equal to 2. So this is a 24 times 12 lattice with alpha equal to 2. And this is a uniform phase, uniform black hole phase, because when I plot the unitarized Wilson line eigenvalues and increase n, the Wilson line phases are basically smeared over the entire circle. And that gets more pronounced as I go to large values of n. So in that sense, this is at low temperature when it is uniform. If it was not uniform, we would see a distribution something like this. So there will be a gap here, and then it will peak only in some finite cut region. But out here, it's a uniform phase. The basic idea, we did a similar study in 2+1 dimensional case, which is more challenging because as you go in higher dimension, your lattice volume, you cannot take much large values of n because of computational challenges. So we tried with n equal to 8. So we took SU8 gauge theory in 3 dimension and tried to reproduce the thermodynamic behavior at low temperatures and at high temperatures. So T is just the dimensionless temperature in terms of 2 coupling. And this is the gravity prediction at small values of T, which is large coupling. And this is the standard high temperature behavior, which goes as TQ. So I mentioned before about the uniform nature, which is again what we see in 3 dimension. So this is the uniform D2 phase with different values of n. But now I also show here what happens in a center symmetric broken phase. Center symmetric broken phase is where there is a gap here. So this is what we call a localized phase. And this is a uniform phase. And there's a transition between these 2 phases, which is dual to the transition between 2 different black hole solutions. And this is what we studied in 2 dimension. And this is clearly understood in terms of the thermodynamic behavior of the system, in the sense that when you go to the localized phase, the prediction is that it should match this curve, which is the orange curve here. And as you go to the uniform black hole phase with gravity prediction, with gravity dual, it should go to this red dashed line. So we see that so the gravity description only is valid to the left of this. And this is the perturbative regime where G is going to 0. So we see that we reproduce the high temperature behavior. And then as we lower the value of dimensionless temperature, we start to tend toward the supergravity results, albeit with a lot of huge errors on the lowest temperature, and that is partly because we are uh, at SU8, and these theories have additional complications of flat directions and metastable vacua, and the errors are huge as you go to lower temperatures. But it seems like there is some agreement, or at least the curve starts to tend from the high temperature behavior, starts to deviate from that and go to the supergravity prediction. This is on a log scale. I just show this on again on a linear scale here, in that this is the high temperature behavior, and this is where we go to low temperature behavior predicted from supergravity. So if we had sufficient large values of n, and if we had sufficient small values of t, we should be exactly on this red dashed curve if the holographic principle is correct. So that is what we checked. So this study is very expensive in 3 dimension, and these results, which I just show in 2 plots here, almost made use of 5 million core hours. And this was done on Fermilab and other Exceed machines over course of several months. So these computations are very challenging. Uh, and even after doing a careful volume extrapolation, the errors, we are not able to reduce the errors a lot, and the agreement is not perfect. So we just get some idea that it is tending toward the exact result, but it's not very precise. So after mentioning about all this, I just want to mention, since I'm already running out of time, I want to mention the future directions which we want to study with our lattice supersymmetric studies. We want to look at the thermodynamics of n equal to 4 superangle theory in 4 dimensions. The temperature dependence in 4 dimensional is trivial, because it's trivial in the sense that it always goes like t to the 4, but the coupling dependence is unknown, at least for finite couplings. And lattice can be a possible tool to do that at finite lambda, because at small and weak coupling, the coupling dependence is known, and at strong coupling, the holography tells us about the coupling dependence, but intermediate couplings have not been explored. Another interesting avenue which we can study using these lattice methods is uh, uh, the idea of Maldacena-Wilson loop. So the Maldacena-Wilson loops uh, is a supersymmetric extension. So unlike the QCD or the usual Wilson loop, where we just have the gauge field A, in the supersymmetric gauge theories, you also have a coupling to the scalars, which are X here. So this is the entire Wilson loop, which is also known as Maldacena-Wilson loop. So this is possible to study on the lattice. So for example, you can study this in n equal to d equal to 4 dimension and lower dimensions, and it follows some non-trivial dependence on the coupling. Another interesting thing is to study static potential in n equal to 4, and this is work in progress which my collaborators are doing, and study scaling dimensions of some simple BPS non-protected operators. So BPS not protected operators just means that as they have some non-trivial dependence on the coupling, while the BPS protected operators don't, their scaling dimensions don't run with lambda. And as I mentioned before, one of the immediate things which we want to understand is how to parallelize our milk-based lattice QCD code over matrix degrees of freedom, even starting with 0 plus 1 dimension as a test case. So those are the future directions, and thank you. That's all I wanted to say.
Great. Yeah, thanks for the very interesting talk. This seems like a really cool program. So yeah, we'll take questions for the speaker now. So just to remind everyone how it works, if you'd like me to unmute you, use the raise hand feature, or if you'd like me to read your question out loud for you, type it into the chat. And yeah, while we're waiting for people to get their thoughts together, did you say what order the transition in the BMN model was?
It is conjectured to be a first order phase transition.
Okay.
Yeah. So it's known to be first order because Yeah, the gravity prediction, the gravity tells you that it should be a first order phase transition, but the order of the phase transition has not been checked at finite coupling on the lattice. So no one has done that yet, because it's we tried doing a finite n scaling test of the order of phase transition, but you really have to be at very large values of n to carefully determine the order of the phase transition. So even in 2-dimension, we don't know order where it should be. It is known what it should be from the gravity calculations, but on the lattice, we cannot determine the order yet. Yeah.
Okay. Is there some well-defined order parameter for it?
Yeah, so the order parameter which I mentioned in this case is the Polyakov loop. We look at the expectation value of the Polyakov loop. So it should be in the large n limit, it should be 1 in one of the phases, and it should go to 0 as you take the large n limit. So that is, for example, if this was at sufficiently large values of n, so it starts with some so this should be exactly at 1 for very small, very large values of n. And if you go to say strong coupling along this axis and increase n, it should go to 0.
Mhm.
That is what it should happen. And going to 0, you can also think about that in terms of, let's say, yeah. So if this becomes completely uniform, it goes to 0 because all the
Yeah. Mhm.
yeah. So that is going to happen at large n. But if you are at sufficiently small values of n, so at finite n, there's not strictly any order parameter, but there's one at large n, which is the
Right.
Polyakov group.
Okay. Thanks. Here, Tom, I'll just unmute you.
Thanks. So it's a very interesting business. So my question, right? I've had bad experiences in n equals 4 in 4 dimensions. What do these lower dimensional models have sign problems?
I don't have a formal proof, but in the sense that the range of couplings which we have explored with the anti-periodic boundary conditions, there at least the phase is that is not a problem for the range of couplings which we have looked into. So, for example, if you compute the phase, it looks to behave like within few percent actually of what we expect. So the phase quenched calculations work perfectly fine in lower dimension for the range of coupling with anti-periodic boundary conditions.
Mm-hmm. Okay.
But if you go to, for example, if you take a supersymmetric preserving boundary condition, you take a periodic boundary condition, then we have a sign problem, very strong sign problem.
Mm-hmm.
But it is in some sense very fortuitous that the holographic conjectures need you to have anti-periodic boundary conditions, and in lower dimension, that also is the place where the sign problem is least problematic in some sense.
And do you have strong coupling phase transitions, which you think are lattice artifact transitions?
So that is certainly, I think, the case in 4-dimensional n equal to 4. But in lower dimensions, if you are at sufficiently large lattices, which we have explored, and at n equal to 8, for the range of couplings, basically, I don't exactly know what happens when you go to very low temperatures, which is like very large lambda. But at sufficiently small moderate temperatures, we don't see a lattice rough like transitions or artifacts like that.
Okay, so that's good. So you can do physics. I mean, that was
Yes,
always
exactly. So the physics we can do definitely in lower dimensions, because I think the thing is that in lower dimension you have more supersymmetry in the sense that in 4 dimension you preserve one nilpotent supercharge, but when you dimensionally reduce to 3 dimension, you preserve 2, because one of the directions is you're reducing along that direction, so that becomes like a site, transforms like a site. So you have 2, and in 2 dimension you have 4 supercharges, so you preserve a max, like more fraction of the original supercharge, and that is also helping with the fine tuning. I think there's a rigorous proof that in 3-dimensional maximally supersymmetric Yang-Mills theories, you don't need any fine tuning if you have at least 2 exact nilpotent supercharges to start off with. That is not the case in 4D.
Okay, thank you.
Are there any other questions for the speaker?
Okay, so we're on the hour, so maybe we'll transition any remaining questions to the Zoom breakout rooms. So thanks again, Raghav, for the great talk.
Yeah,
So
thank you.
everyone, if you'd like to stay around to chat more with Raghav, please stay on the line. Otherwise, see you next time.